In this module, we are going to take some time to talk about probability distributions. These are very similar to the histograms that we've previously discussed, but instead of the bars representing the frequency in which observations fall, the heights of the bar or the height of the line in terms of continuous distributions is now going to represent the probability that an observation falls within a given bin. What we are going to do here is we are going to revisit the definition of continuous and discrete variables, and then we are going to talk about how to interpret probability distributions. From the terminology section, we can see that discrete variables take one of a countable set of outcomes. For instance, in a heads versus tail coin flip, there are only two outcomes, heads or tails. In contrast, continuous variables can take any number of values from an uncountably infinite set of possibilities. The defining characteristics here are that if you give two valid values from a continuous distribution, I can give you a value that falls in between them that is also valid. For instance, how late is an employee to work? Well, an employee could be 1 minute late to work, or maybe could be 2 minutes late to work. But note that any value in between is also valid. An employee could be 1.5 minutes late to work, or 1.25 minutes late to work. This is going to play a role when we talk about how to plot the probability distributions. In particular, choosing whether we are going to use a probability mass function or if we are going to use a probability density function. Let's revisit histograms that you've seen in the histogram video that you watched earlier. On the left, we have plotted a histogram of the outcomes for 20 trials, where in each trial we flipped a coin twice. Now, the possible outcomes for each trial are that you either get no heads, 0, one head, represented by 1, or two heads, represented by 2. The height of these bars represent the number of times that this outcome occurred within these 20 trials. On 5 of the trials, we received no heads. On 10 of the trials, we received one head. And on 5 of the trials, we received 2 heads. We also created a histogram for employee tardiness, which is a continuous variable. Here we can see the number of employees whose lateness was within the range of each bin. For instance, we can see 26 employees in the bin going from -1 to 0, representing employees that were at most 1 minute early or on time. Now, this can be very helpful when what we want to know is simply the counts for a current sample. The limitation comes in if we actually want to understand the probabilities when we are extending it to talking about population characteristics. For instance, instead of knowing that 5 trials in the coin flip example came up with no heads, it might be more helpful to understand the proportion of times that happened. This helps thinking about what might happen in a population that is conceivably larger or in a sample with a different size than the one we had in our analysis. Now let's take a look at what these plots would look like if they were probability distributions instead of histograms. The probability distribution plots actually have two different names depending on if it's a discrete or if it's a continuous variable. For discrete variables, they're known as probability mass functions, and for continuous variables, they're known as probability density functions. In either case, what they do is describe the data's range and probability. The distinction here is that the histograms were describing the data's range and frequency in our sample. Here we have the probability distribution, so it described the range and probability, not frequency. We can see that the plots actually look very similar with a couple of slight changes. Starting with a discrete variable, the number of heads arising from 2 coin flips is plotted on the left, and we can see that the only real change is that instead of the y-axis representing the counts, it now represents probabilities. Before we had 5 out of 20 trials that produced no heads. Here we are going to say that 25% of the trials produced no heads. We can also say that we have no heads with a probability of 0.25. It's a very simple transition here. Moving over to the continuous variable on the right, we're going to look at the probability density function related to employees' tardiness. Now, again, the y-axis represents the probability density. However, we no longer see bars like in the histogram case. What we see instead, it's a line that represents the probability at each one of the intervals. Now, why is this a line? It's a line because we have a continuous variable. Remember that for any two valid values in the distribution, I can give you a valid value in between those two. Well, that's going to apply when we plot the probability density function. If I take two close points on the domain of the distribution, for instance, -4 and -3.5, I can find values in between and see the corresponding probability density on the curve. Now, there are a couple of important attributes related to probability distributions. One, the values can never be negative. That is to say that the line for probability density function can never fall below the x-axis. And none of the bar for the probability mass function can fall below 0. Similarly, the total probability must sum to 1. That is to say that some outcome must occur with certainty, which is what the probability of 1 represents. I can also say that there is 100% probability that something happens. So if you add up the height of all the bars on the left, the total will be 1. In this case, 0.25 plus 0.5 plus 0.25 equals 1. On the probability density function on the right, it is the area under the curve that is equal to 1. It also means that some value must be observed with 100% probability. For those of you who are familiar with calculus, you'll recognize this as the integral. For those of you who are not familiar with calculus, well, please review calculus, and for now, just take my word for it. Now, let's discuss how we can interpret probability distributions. First, we'll return to histograms. Remember that with histograms, we can aggregate observations over a range to count the frequency over several different bins. If we turn to our coin flip example, if we want to know the number of trials that produced at most one head, that means produced either 0 heads or 1 head, all we have to do is add up the height of the bar at 0 and at 1. In this case, that's 5 plus 10 equals 15. We can do something very similar for the histogram of employee tardiness. Say, for example, we wanted to know the number of employees that were less than 1 minute late to work. Well, all we have to do is add up all the bars representing employees that were less than 1 minute late to work. So we have the first bar, which is between -3 and -2, but not including -2. Then the second bar is from -2 up to -1, but not including -1. Then the bar between -1 and 0, and the bar between 0 and 1. So if we add up these 4 bars together, we find that 64 employees were less than 1 minute late to work. When looking at probability distributions, we can also aggregate probabilities over ranges. Say, for example, instead of wanting to know the number of trials in our sample that produced fewer than 2 heads into coin flips, we wanted to know the proportion of trials in our sample that produced less than 2 heads into coin flips. So instead of looking at the number, we are looking at the proportion. Well, we can do something very similar to what we did with the histograms. That is, we are simply going to add the heights of the bars at 0 and the bar at 1. That is, in this case, 0.25 plus 0.5, and we find that 75%, or a probability of 0.75, of a trial produced at most one head. Now we can turn to the continuous distribution, represented by the probability density function for employee tardiness on the right. If we wanted to know the probability of an employee being less than 1 minute late, well, there aren't any bars that we can add together. Instead, what we're going to do is take the area under the curve over that range. In this case, that range is going to go theoretically from minus infinity to 1. From what we see on the graph, most of the area under the curve starts after minus 4, so we are going to integrate between minus 4 to 1. When we take that integral, we find that the probability of an employee being less than 1 minute late is 0.84. So there are 84% chance that an employee is less than 1 minute late. The nice part about this is that the proportions allow us to say something about what we believe will happen in the population based on a sample, even if the two sizes, the size of the population and the size of our sample, are very different.